Welcome, curious minds. Today, we're embarking on a deep dive into something, well, utterly fundamental to how we see the world. Light.
That's right.
Specifically, how it behaves when it, bumps into things or passes through them. It's not always as simple as it seems, and frankly, light can be a bit of a trickster. Our journey today will be guided by a collection of practice questions and answers on reflection and refraction of light. We're using them as a sort of practical roadmap.
Yeah, a roadmap to uncover the, let's say, surprising truths behind these everyday phenomena.
Exactly.
We're going to demystify how light bounces and bends, moving beyond just the textbook definitions to explore the elegance and precision of these physical laws.
Right.
You'll hopefully walk away with a deeper appreciation for the optics that shape our visual world.
Yeah, get ready for some genuine aha moments as we unpack light's peculiar habits. So let's kick things off with reflection light bouncing off a surface. It seems straightforward, right?
Mostly, yeah.
But okay, what happens if a ray of light hits a mirror head on? Like perfectly perpendicular to the surface, you might think it just, disappear. But the physics is more precise.
Well, what's truly fascinating here, and it is a bit counterintuitive, is that even then, the laws of reflection hold perfectly.
Yeah.
When a light ray hits a surface perpendicularly, its angle of incidence is actually 0 degrees, relative to the normal, that is.
0 degrees, right.
Because of this, it reflects straight back along its original path. Think of it like throwing a perfectly straight ball at a wall. It comes straight back to you.
Okay, that makes perfect sense once you think about the angle of incidence, really meaning the angle relative to the normal, that imaginary perpendicular line.
Exactly.
So speaking of those, what are the fundamental rules? The laws that govern all reflection, whether it's perpendicular or, at an angle.
The laws are elegantly simple and incredibly powerful. First, the angle at which light strikes the surface, that's the angle of incidence, is always exactly equal to the angle at which it bounces off.
The angle of reflection.
Precisely. Angle in equals angle out. Second, the incoming ray, the outgoing reflected ray, and that imaginary line, the normal, they all lie perfectly in the same flat plane.
Okay, so they're not like twisting off in different directions.
No, not at all. These aren't just academic rules. They're the blueprint for, well, everything from designing a sophisticated telescope to making sure your car's headlights work effectively.
That precision is what's so compelling.
Mm.
And when we talk about real-world applications, beyond just, looking at ourselves in a flat bathroom mirror, where do we see these principles really leveraged daily?
A fantastic example from our materials is the concave mirror, specifically the kind you find in, say, a torch or a car headlight.
Right, the curved ones.
Exactly. They curve inward. They're meticulously designed to collect light from a bulb, and then, using those precise laws of reflection,
Angle in, angle out.
they focus it into a powerful, often parallel beam. It's all about manipulating those bounce angles to get a specific effect.
And these curved mirrors, they can create some really intriguing images, can't they? Depending on where the object is placed.
Absolutely.
Our materials describe a unique scenario. What happens when an object is placed exactly at the center of curvature of a concave mirror? That sounds specific.
It is a very special point. If an object is placed precisely there, at the center of curvature, the image forms right there too, same spot.
At the center of curvature as well?
Mm-hmm. It's also real, meaning it could be projected onto a screen. It's inverted, so upside down.
Okay.
And critically, it's the exact same size as the object, 1-to-1 size.
Wow. That's useful.
Incredibly useful in optical instruments, yeah. For instance, when you need to project an image with precise sizing or in certain measurement devices, it's a very predictable outcome of those reflection laws.
So reflection is all about the bounce. But here's where, for me anyway, it gets really interesting. What happens when light doesn't just bounce off, but actually plunges into a new material, like moving from air into water or, say, glass? That's where things get bent out of shape, literally.
Yeah.
What exactly do we mean by the refraction of light?
Right. Refraction is basically the bending of light as it passes from one transparent medium into another one.
Bending.
Well, it bends because the light actually changes its speed.
Changes speed. Okay.
Yeah. Imagine running across pavement and then suddenly hitting thick mud.
You'd slow down.
You'd slow down, and if you hit the mud at an angle, you're going to veer off course, right? Light does something very similar when it enters a different medium.
And what causes that crucial change in speed? That mud effect that makes the light bend?
The underlying cause is a change in what we call the optical density of the medium.
Optical density.
Yeah.
That like physical density, how heavy it is.
Not necessarily. It's related, but it's more about how much the medium sort of interacts with or resists the light passing through it, slowing it down. Air, for instance, is optically less dense than water or glass. That means light travels faster through air. When light moves from a faster medium to a slower one at an angle, it bends.
That brings us to a key concept then, the refractive index. I've heard that term. What is it, and why does it matter so much for understanding light's behavior?
Right. The refractive index, usually written as N, it's essentially light's personal speedometer for any given material.
A speedometer for light?
Kinda. It quantifies how much a medium slows down light compared to light's maximum speed, which is in a vacuum.
Okay.
It's a simple ratio. Speed of light in a vacuum divided by the speed of light in that specific medium. So a higher refractive index means light travels significantly slower in that material.
And therefore?
And therefore, it will generally bend more when entering that material from a faster one. This is why a diamond, which has a very high refractive index.
Sparkles so much.
Exactly. It bends and internally reflects light intensely, creating that sparkle.
Okay, let's try and visualize this bending more concretely. Our sources describe what happens when a ray of light passes obliquely, meaning at an angle, right?
Yes, not straight on.
From air into a denser medium like glass. What does it look like?
So when light transitions from a rarer, faster medium like air into a denser, slower medium like glass, it slows down.
Mm-hmm.
And because it slows down, it bends towards the normal, towards that imaginary perpendicular line.
Towards it, okay.
So the angle inside the glass, the angle of refraction, becomes smaller than the angle it made out in the air, the angle of incidence.
And if it goes the other way, glass to air.
Then the opposite happens. It speeds up and bends away from the normal.
So there's a precise, predictable relationship governing this bend. It's not random.
Not at all.
And our sources even mention Snell's law, which, puts numbers to this. Can you give us the conceptual takeaway without getting us too bogged down in the math itself?
Absolutely. Snell's law is the key formula here. It basically tells us there's a consistent proportional relationship between the angles, incidence, and refraction, and the refractive indices of the two materials involved.
So it connects the angles and the speeds, essentially.
Precisely. It's the formula that allows engineers and scientists to predict exactly how light will bend. It's crucial for designing everything from eyeglasses and camera lenses to microscopes and telescopes.
Oh.
So if you know the refractive indices, how fast light travels in two materials, Snell's law gives you the exact recipe for how much it will bend when it crosses from one to the other at any given angle. It's all about that predictable balance.
Okay, that makes sense. And sometimes light doesn't just bend and continue. It can also get slightly shifted from its original path. Our sources mention something called lateral displacement.
Ah, yes, lateral displacement.
What exactly is that, and what factors influence how much it shifts?
Lateral displacement is basically how much a light beam gets shoved sideways when it passes through a transparent material with parallel sides, like a thick pane of window glass or a glass slab in a lab.
Shoved sideways.
Okay. Imagine the light ray going in, bending, traveling through the glass, and then bending back out parallel to its original direction. Lateral displacement is the perpendicular distance between that original path and the final emergent path.
Right, so it's parallel but offset.
Exactly. And how much it gets offset, that shift, depends on three key things. The thickness of the slab.
Makes sense. Thicker slab, more shift, maybe?
Generally, yes. Also, the angle at which the light initially strikes the slab, the angle of incidence. A steeper angle usually means more shift.
Okay.
And of course, the material's refractive index. A higher refractive index will also cause more displacement, all else being equal. That's why looking through a really thick piece of glass can sometimes make objects appear slightly shifted from where they actually are.
So we've unpacked the individual behaviors of light bouncing and bending. Now let's try and connect these dots, see how these principles apply in maybe more complex scenarios, even things we take for granted.
Good idea.
Let's revisit a concave mirror. Our materials describe an object placed 20 centimeters from a concave mirror that has a focal length of 10 centimeters. What does that specific setup tell us about the resulting image?
Okay, this is a classic setup, and it reveals a really powerful property we touched on earlier.
How so?
Because the object distance, 20 centimeters, is exactly twice the focal length, 10 centimeter.
Distance equals 2 times focal length.
Right. That means the object is placed precisely at the center of curvature of the mirror.
Which we talked about.
Exactly. And as we discussed, when an object is at the center of curvature, what happens?
The image forms there too. Same spot, same size, but inverted and real.
Bingo. The image also forms at 20 centimeters. It's real, inverted, and perfectly the same size as the object. This particular setup is super useful in, say, optical systems where you need a one-to-one reproduction of an image.
Like in some copiers or projectors, maybe.
Certain types, yes, or specific scientific instruments. The math involved, using the mirror formula, simply confirms this elegant, predictable behavior based on those fundamental reflection laws.
That's a great example of how consistent these laws are. The rules predict the outcome. Now, for one of those truly classic aha moments, that shows how fundamental these principles are in just everyday life. Why does a pencil appear bent when you dip it in a glass of water?
Yes.
It's such a common thing we barely notice it, but the physics behind it is quite profound, isn't it?
It really is. This is a perfect everyday demonstration of refraction playing tricks on our eyes.
How does it work?
Well, when you look at the pencil in the water, light rays are traveling from the submerged part of the pencil.
Right, from the pencil itself.
They travel through the optically denser water, then cross the boundary into the optically rarer air before finally reaching your eyes.
Okay, water to air, denser to rarer.
And as they make that transition, remember what happens. They speed up and bend away from the normal.
Away from the normal. Got it.
Now, your brain doesn't know about Snell's law or refractive indices. It's wired to assume that light always travels in straight lines.
Makes sense. That's how we usually see things.
So it takes those bend rays hitting your eye and traces them back in a straight line to where it thinks they originated from.
Ah.
And because the rays bent away from the normal, tracing them straight back makes the submerged part of the pencil appear higher up, shallower, and therefore displaced from its actual position.
So it looks like it snapped or bent at the waterline.
Exactly. It's a pure optical illusion created entirely by the changing speed and bending of light as it moves from water to air. Amazing, isn't it?
That really is amazing how our perception is kind of tricked by these simple physics rules.
Yeah.
And thinking about light being guided or even trapped, how do these principles play out in something like fiber optics? They're everywhere now, right? Internet cables, medical scopes.
Oh, fiber optics are a brilliant application, primarily of reflection, but in a very specific way. It relies on a phenomenon called total internal reflection.
Total internal reflection. Okay, what's that?
Imagine light already inside an optically dense material, like the glass core of a fiber optic cable. If that light hits the boundary between the dense core and the less dense outer layer, called the cladding, at a very shallow angle.
Shallow, meaning almost parallel to the surface.
Exactly, beyond a certain critical angle. Instead of refracting out into the cladding, the light doesn't escape at all. It gets completely reflected back into the dense core.
Completely reflected, like a perfect mirror.
Essentially, yes, but without needing a mirrored surface. It's a property of the light hitting the boundary at that shallow angle from the denser side.
Wow.
This happens over and over again. The light bounces along the inside of the fiber, zigzagging down its length, effectively trapped within the core.
So it just keeps reflecting internally.
Mm-hmm. And that's how information, encoded as pulses of light, can travel for miles and miles through these tiny threads with very little loss of signal. All thanks to light being repeatedly and totally internally reflected. It's really the ultimate expression of manipulating light's path using these basic principles.
Incredible. So what does this all mean then? We started by, unpacking basic questions about how light bounces and bends.
Reflection and refraction.
And we've now seen how these fundamental principles explain everything from how a simple torch focuses light to why a pencil looks bent in a glass of water, and even how the entire internet can travel through tiny glass threads.
It really does. This deep dive, I think, highlights the elegant precision with which the laws of physics govern light's behavior. Understanding reflection and refraction isn't just about, formulas or definitions you memorize for a test.
Right.
It's about comprehending the very fabric of how we perceive the world, how visual illusions work, and how countless technologies, from simple mirrors to complex fiber optics, are designed specifically to manipulate light for our benefit.
It's pretty incredible how much insight we could get from just looking closely at those practice questions and answers, really digging into the why behind them.
Absolutely. And this raises an important question, maybe a final thought for you, our listener.
Yeah.
Now that you understand a bit more about the mechanics of how light interacts with different media, bouncing, bending, changing speed, pause for a moment. Look around you. Consider other common optical phenomena you encounter every single day.
Like what?
Well, How might the principles of reflection and refraction be at work in the vibrant colors of a rainbow after a storm? Or in the lenses of your eyeglasses if you wear them? Or even that shimmering mirage effect you sometimes see above a hot road surface in the summer?
Good examples.
There's always more to observe and connect. Think about how these powerful scientific principles of light are playing out right in front of you, shaping your everyday experience.